Let's solve another pump problem. This one will be a pump that pumps water up a hill and then out through a nozzle. A pump working under steady state conditions draws water from a large reservoir. The water travels from the reservoir through the pump and out a hose with a nozzle on the end of it. The horizontal nozzle is 10 meters above the reservoir from which it is drawing water. The temperature and pressure of the water in the reservoir are 20 degrees C and 1 bar, respectively. The diameter of the inlet pipe is 20 centimeters, and the volumetric flow rate at the inlet is 0.1 cubic meters per second. The nozzle's exit has a diameter of 2 centimeters. The water remains at a constant temperature throughout the system. Determine A, the velocity at the inlet in meters per second, B, the velocity at the outlet in meters per second, and C, the power required by the pump in kilowatts. Let's draw a schematic of this situation. We have a pond, and for elevation, we'll consider the surface of the pond our datum, where the elevation is 0. So we're drawing water out of the pond through a pipe into the inlet of a pump, and then it flows through a pipe or hose until it gets up the hill. And then at the exit, water is discharged through a nozzle. So if we blow up this exit and look at where state 2 is, state 2 is defined at the very tip of the exit. It's where the water comes back into the atmosphere. Let's look at what we're given. The inlet pressure, or I should say the pressure at state 1, is 1 bar. Well, let's look at that. We're setting state 1 just inside the inlet pipe, right at the surface of the pond. Now, at the surface of the pond, there's no pressure on the surface from water. The only pressure at the surface is from the atmosphere. So essentially what this problem is stating is that the atmospheric pressure is being taken as 1 bar. The temperature of the water in the pond is 20 degrees C. The volumetric flow rate through the pipe and pumping system is 0.1 cubic meters per second. The inlet diameter is 20 centimeters and the inlet elevation is 0. Now state 2, the pressure is also given as 1 bar. And again, that is because state 2 is where the water re-enters the atmosphere. So it may have a high velocity coming out of this nozzle, but it has no static pressure other than the atmospheric pressure. And the temperature, we were told, does not change. It's 20 degrees C throughout. The diameter at the state 2 is much smaller than at the inlet. It's only 2 centimeters. And the elevation is 10 meters. We're going to model this as an open system operating at steady state. We were told that it was an adiabatic system. In other words, there's no heat transfer between the system and its surroundings. The water is a subcooled liquid at constant temperature, and therefore it's a constant specific volume. We want to find the velocity at the inlet and the velocity at the exit, both in meters per second. And we want to find the power requirement of the pump in kilowatts. Let's draw a property diagram. So this will be a TV diagram. And we know that at both states, the pressure is 1 bar. Now, the pressure is higher than 1 bar between the pump and the exit, and it's lower than 1 bar between the inlet and the pump. But we're only interested in the pressure at the inlet and at the exit, and both are atmospheric pressure, so they'll be 1 bar. And on a TV diagram, since state 1 and state 2 are at the same pressure and also the same temperature, then the states are identical. The same temperature, the same pressure. So let's begin solving this problem with a continuity equation. We know that the mass flow rate is area times velocity divided by specific volume. But area times velocity is just the volumetric flow rate. So we have that the mass flow rate is equal to the volumetric flow rate divided by the specific volume. And we'll evaluate this at the inlet state. So We can go to the water saturation table at 20 degrees C, and for a subcooled liquid, we'll take the specific volume at state 1 to be the specific volume of a saturated liquid at the same temperature, which is 20 degrees C. And from our table, we get that the specific volume is 1.0018 times 10 to the minus third cubic meters per kilogram. And we can do this because we're considering the liquid to be incompressible. So now we say the mass flow rate is just the volumetric flow rate, which was a given value, divided by the specific volume, which we just found in the table, and we'll calculate a mass flow rate of 99.82 kilograms per second, which allows us now to calculate the inlet velocity. It's just the mass flow rate, which we just calculated, times the specific volume, which we just got out of the table, divided by the area at the inlet. Well, we know the diameter at the inlet is 20 centimeters. So the area is just pi over 4d squared. We have to convert square centimeters to square meters, and we get a velocity at the inlet of 3.19 meters per second. We'll use exactly the same calculation to find the velocity at the exit. It's just mass flow rate times the specific volume times the area. Well, we know the specific volume at the exit is the same as at the inlet. It's at the same temperature. It's also at the same pressure, although that wouldn't matter as long as we're invoking the incompressible fluid model. So we're going to write the exact same equation except for the area, which is 1/100th of what it is at the inlet. And so we calculate that the velocity of the exit is 100 times greater than it was at the inlet. We can now write an energy balance. We know that for an open system operating at steady state, dEdt is always 0. And that's equal to Q dot minus W dot plus M dot times the quantity, the change in enthalpy, the change in kinetic energy, plus the change in potential energy. We were told this was an adiabatic process, that there was no heat transfer between the system and its surroundings. So we'll eliminate that term. So now let's calculate these delta terms in our energy balance. The first is the change in enthalpy, delta H. And we know for a subcooled liquid, delta H is just C delta T plus V delta P. Well, there's no change in temperature and there's no change in pressure. The inlet and exit pressures and temperatures are identical. So delta H is 0. How about kinetic energy? That term is V1 squared minus V2 squared over 2. We calculated the initial and final velocities. We do end up with terms or units of meters squared per second squared. And previously we had derived this unit conversion that 1,000 meters squared per second squared is equivalent to a kilojoule per kilogram. If you want to find that for yourself, you can multiply meters squared per second squared by kilogram over kilogram, and you'll get this conversion factor. We see that the change in kinetic energy is minus 50.84 kilojoules per kilogram. Let's calculate the delta PE term. It's just the acceleration of gravity times Z1 minus Z2. We'll take G as 9.81 meters per second squared. Z1 is given as 0 meters, and the elevation at state 2 is 10 meters. And again, our conversion factor, and we get that the change in potential energy is minus 0.0981 kilojoules per kilogram. Well, now we have everything we need to solve the energy balance. We'll rearrange what we had in this balance and solve for the power, and W dot is equal to M dot times delta H plus delta KE plus delta PE. We calculated the mass flow rate, and we just calculated each one of these terms. And we solve this problem and get W dot is minus 5084 kilowatts. The negative indicates that unlike positive power, the system does not put out power. It requires power being put into it in order for the steady state process to take place. So we would fully expect a negative W dot in this term. It is the power requirement of the pump.